Sorry, y'all, my video cut off right there when I was talking about this ln of b. What I was saying was that um, you might get a little confused when you see this because this is actually the b, the century factor. So it's not the original b that we had from the problem, it's the b to the 100th. So remember, that's what I actually computed, was ln of b to the 100th, and this is the same computation. Okay. All right, just wanted to point that out. Oh, and then the other thing is that the method of solution that's given in the problem here is a bit different than the way I went about this, solving this problem. I did it in an annual way, so I did, I put this in as years, a full 6,000 years. The other way you could do this is you could go ahead and do your century conversion. So instead of doing 6,000 years, you could do 65.63. Okay, and then that's what's happening here. Then your exponential regression will automatically be in terms of centuries. So in some ways that's easier, actually. Now, of course, I've already drug you through this method of solution where we did the conversion. If I had converted it to centuries in the beginning, then it would have been a little bit more direct, our solution. So as you can see here, when you do your regression in terms of centuries, you automatically get the century factor, and then you just subtract 1 from that factor, and then that's the answer that we got. And then when you convert it to continuous form, you really can just take the natural log of just the factor that's in your model. So that's why I had to do b to the 100th, whereas here it just has ln of b. Either method is fine as long as you understand what you're doing, okay? Okay. Yet another way of doing this would be to use this formula, but you know what? I'm not even going to bother. If you want to use this formula, then please read this slide and you can do it, but I think we've spent enough time talking about this one. Let's look at a new problem. The number of bacteria in an exponentially growing culture increased by a factor of 5 in 19.25 hours. And then we've got a whole bunch of questions about this. So first of all, we need a model. And we are given this kind of weird piece of information. We're used to having a doubling time or a half-life, but this is growing, but instead of giving a doubling time, we've given a quintupling time, right? So we've multiplied it by 5. However, I'm still going to treat this the same way that I would treat it if I'd been given a doubling time. So I'm going to put 19.25 here. I'm going to assume I started with 1, and then I'm going to end up with 5. And that will get me my factor. And from that I can get the rate and whatever else I need. You might actually, if you read the questions, you might see this doubling time question and kind of freak out. Notice that I didn't even look at the question before I started finding the model. And it actually is better to do that because the question is just going to confuse me. I need to get the model first, and then I can worry about the question. So that's my advice. Okay, so L1 is 0 and 19.25. And we're going from 1 to 5. And then I'm going to do exponential regression. And there's our model. So our factor is 1.087. Okay, so now I can look at this question. What is the doubling time? Well, the doubling time is, how long it takes to double the initial amount. So if I started with 1, then I want to know how long it takes me to get to 2. So that's going to be calc intersect. And also I can kind of guesstimate this. If it quintuples in 19.25 hours, then definitely the doubling time is less than 20. So I'm pretty safe doing that. And let's do zoom fit. Okay. And our doubling time is 8.29 hours. All right. What is the hourly growth rate? Well, we're already in hours, so we don't have to change the time unit, so that's nice. But I need to subtract 1 from the factor. Multiply by 100, and it's 8.72%. Okay. Now the continuous hourly growth rate, we're converting from standard to continuous. So the conversion, the formula is RC is ln of B, ln of the factor. A lot of times people will mess this up and take ln of the rate. It's ln of the factor. So ln of vars, y var, statistics equation number 3 is B. And then I'm going to go ahead and multiply that by 100. So it's 8.361. 8.361%. That's my continuous hourly growth rate. Okay. Once again, if you wanted to do this using the new old formula, you certainly can, and this slide explains how you would go about that. And that brings section 5.4 to a close. All right, thanks.